Hello, everyone. Thank you for joining me today. This is Muhannad Al-Hamid, and I will be presenting our ICML 2024 paper on loss landscape visualization titled the Neuro-Visualizer. This research was done as part of my PhD at Virginia Tech and under supervision of Professor Anush Karpatnaik. So, without further ado, let's dive into it. So, let's first entertain the research background of our work. We know that neural networks have been gaining unparalleled popularity in the last couple of decades. And they are also becoming larger so they could model more complex phenomena. We also know that there is a great interest in understanding how these neural networks work, including efforts towards interpretability and theoretical guarantees. However, such guarantees are becoming harder to obtain quantitatively as these models grow in size. As such, it has recently become more popular to attack this problem from a qualitative perspective, and that would be through visualizations of the loss landscape. Using these visualizations, researchers have been able to reveal much about the model's generalization performance and training convergence. Current approaches visualize 2D slices of the high-dimensional space. So, for example, here we have a heat map visualizing the loss as a heat map on a 2D grid. But this leads to limitations and inaccuracies. For example, trajectories generally do not lie on a 2D plane. Also, it is not clear exactly how to choose the slice or the scale of this visualization. So, in this work, our first goal is to propose a modification to current loss landscape visualization methods that addresses these concerns. Now, to later test the capabilities of the proposed visualization method, I choose KGML, Knowledge-Guided Machine Learning, as an application. KGML is a domain I have been researching in the past few years. It is a framework where neural networks are designed such that, in addition to the training data, they take into account expert domain knowledge. This framework has shown great success at enhancing model generalizability, and it has been applied in many fields, including physics for solving partial differential equations, for example, and in biology for species image generation. Though despite KGML's success as a framework, it is still not clear how adding knowledge-guided loss functions affects the loss landscape of a neural network, and how that subsequently impacts model convergence. In this paper, we consider investigating this gap to be an important endeavor, and we work towards it. So, given the two problems we just mentioned, our research here has two goals. First and foremost, we address the limitations of existing loss landscape visualization methods and devise a new approach to address these limitations. And second, we also prove the efficacy of our new method by applying it to some KGML models, thus gaining a better understanding of the framework's effect on the loss landscape. So, how do we improve on the existing visualization method? Well, we noticed that these methods extract 2D planes, and as we said, high-dimensional trajectories do not fit on a 2D plane. So, for example, here we see a trajectory, and it clearly does not fit on the plane. But they do fit on 2D manifolds, and that is the key to our solution. And since current approaches use PCA to select the 2D slice, we need to use something different, something nonlinear. And as such, we decide to use an autoencoder. So this is how the Neuro-Visualizer is born. Putting it succinctly, an autoencoder is used to learn a 2D embedding that is sufficient to reconstruct the trajectory in high dimensional space, which is the original space. Once the training is done, the 2D embedding can be traversed and sampled as a grid to be visualized. Each point on the grid can be reconstructed in high dimensional space, and then that reconstruction is used to calculate and visualize the loss heat map. And that's how our nonlinear loss landscape visualization method learns a manifold as opposed to a 2D plane that better fits the trajectory of interest. Finally, one advantage to using an autoencoder is that it allows us to add other optimization constraints to mold the manifold as we desire. For example, given the following visualization, we can choose to retrain our autoencoder such that it may pin the first and last models in the trajectory to the corners of the grid, which unfolds the trajectory and offers better visualizations. Or it can be retrained such that it dynamically adjusts the scaling of the grid, allowing us to investigate how well regularized the lost surface is, which is important when it comes to studying model optimization. Now, now that we have explained the method itself, let's take a look at some of the results we have. If we take coffee PGNN, a KGML model that performs eigen decomposition as an example, and visualize its loss landscape using both PCA and the Neuro-Visualizer, we can see that the latter offers much richer details. More specifically, we can see that what looks like a simple minima here using PCA is actually a loss landscape that is riddled with many local minima. Quantitatively, if we compare in terms of the relative error in the loss values and the projection error in the high dimensional space, we see that the Neuro-Visualizer has much lower error by orders of magnitude compared to both linear and nonlinear methods. This proves that our method provides a much more faithful visualization than others. Moving to another application in KGML, we consider using Neuro-Visualizer to study the loss landscape of physics-informed neural networks, or PINNs. In this experiment, we consider convection PDEs and vary their beta. Research has shown that such PDEs with high beta values tend to be difficult to solve with PINNs. So when we train different PINNs with different betas and plot their loss landscapes using Neuro-Visualizer, the story becomes clear. As beta increases, the loss landscape becomes more complex and ill-regularized, which in turn affects the optimization process negatively. Another experiment studies the impact of changing the weight balancing technique used to train the PINN. For example, one could use constant weights, grad normalization, or learning rate annealing. So the question is whether any of these techniques clearly outperforms the rest. For example, some researchers have suggested that using learning rate annealing achieves better results when solving the Helmholtz equation. While plotting the loss landscape shows that different weight balancing techniques converge to different minima, it is not clear that any specific technique is superior, implying that not all PDEs benefit from learning rate annealing equally. While we chose to highlight only a couple of experiments in this video, please visit our paper and GitHub repo for an expanded discussion with more experiments. Thank you again, and if you have any questions, please don't hesitate to reach out. Enjoy the conference.